Welcome back, my friends, to the show that never ends. We're so glad you could attend. Come inside, come inside. There behind the glass stands a real blade of grass. Be careful as you pass. Move along, move along. Come inside, the show's about to start. Guaranteed to blow your head apart. Rest assured, you'll get your money's worth.
Hello and welcome to another episode in our continuing series of MetalForming Live, where our editorial team here at MetalForming Magazine recruits expert panelists to discuss all the important issues that metal formers and fabricators are dealing with today. So I'm Brad Kuvan, editorial director of MetalForming Magazine, here live with you from the headquarters of the Precision Metal Forming Association. And I, along with our senior editor, Lou Kren, are happy to welcome you to today's session, which is called The Science of Forming, Tackling Higher Strength Materials. We've got a really high-level expertise panel ready to discuss this topic with you all. Before we get started, first and foremost, I want to thank our generous sponsors for their support. Without their sponsorship dollars, we wouldn't be able to bring you such valuable content in such an easy to digest format that we're bringing you today. So our sponsors for the session today are Stamtec, Shea Presses, Nidec Press and Automation, and Principal Financial. So again, thanks to all of these companies for their support. In addition, as we always do, I want to stress to the audience online that these live discussions are really meant to generate ideas from you, our guests, to bring to your company so that you can improve operational performance, productivity, and quality. So our panelists are here with you today to answer your questions and discuss your ideas. So please, as you're listening to them present on this topic, jot down some questions, use the Zoom panel, the Q&A panel on Zoom to ask your questions and participate in these discussions. We've got lots of time to address all the questions that you might have. So without further ado, let's go ahead and meet the rest of our panelists. I'll start with our senior editor, Lou, on the end, and we'll work our way over.
Hi, Lou Kren, senior editor with MetalForming Magazine.
Good afternoon, my name is Vince Miliota. I'm with Martin Maria International.
Hi there, my name is Danny Schaeffler with Engineering Quality Solutions, a metal formability consulting firm.
Good afternoon. My name is Art Hedrick, and my company is called Diology, which specializes in training and consulting for the tool and die and sheet metal stamping industry.
Thanks, guys. And yeah, so Danny wrote for us for many years in the past and continues to write some articles. And Art is the newest member of our editorial team, writing regular column for us as well. So we thank you for your contributions to the magazine and the PMA, and welcome Vince, and try to get you more involved in what we're doing here. As well. So again, thanks for the panel for being here today with us live. Before we get started, please enjoy this brief sponsorship video from Shea, and then we'll kick off our panel discussion.
What Shea can offer you from a sales perspective is a couple of things. One of them is get to know you. Who are you? What are your business needs? What are the upcoming challenges that you may face? And how Shea can provide you with a full turnkey project.
It's a very large company, but with a small company feel to it. We have a lot of flexibility and capabilities for both our domestic side here at Shea America, as well as the support from our corporate overseas. We can really offer our customers a great value for our products to help them optimize their production, their ROI on the equipment they purchase.
What I feel that makes Shea unique is the fact that we basically try to help the customer, we help think for them and try to benefit what their needs are or anticipate what they need so that we can better serve them.
Shea has a very good product. We have the full complement of presses from 28 ton all the way up to 2,500 ton presses, and we have a full complement of parts in-house in Tennessee, and also have service technicians readily available to service all of our equipment.
And typically whenever we receive a call for parts, we can get them out same day. We have probably 95% of the parts here in Tennessee and Mexico.
Shea has a very strong service department, very strong service team. We're able to resolve the issue for the customer so that they can continue making parts and continue on with their production.
From the point of finding a press project all the way after installation of the press project, we have excellent people at the factory, we have excellent people in the US, we have excellent people in Mexico that will help me help you become a satisfied customer.
All right, so to kick off our panel discussion, I'm pleased to turn the stage over to Art Hedrick, who's really gonna present a few slides. It's gonna lay the groundwork for the rest of our session today. So Art.
Super. Well, hey, thanks, Lou. And special thanks to all the folks here at Precision Metal Forming Association for inviting me to be part of this conference. It's very flattering. And also including me as a columnist in the Metal Forming magazine to take over Dr. Stuart Keeler's column of the science of metal forming. It's truly flattering for me and very humbling. He's got some big shoes to fill. I feel anyway. So anyway, thank you for that. Before we get going here, I want to give you a first virtual training tip, and that is to blow across the top of your rum and coke so that the attendees think your coffee's hot. It's just coffee. Okay. I'm going to start my presentation here. I've only got just a short period of time, and I'm going to get on my soapbox a little bit here. Any of you who have attended any of my conferences, either at your company or public conferences, you know how I feel about the tool and die industry. I'm very passionate about it. And so I'm going to start off with talking a little bit about paradigms. You might think, well, hey, this is a metal forming conference. What are doing talking about, human psychology? Keep in mind that everything we do, every thought we have, every emotion, every perception we have begins with a thought, how we see things, okay? A paradigm is simply defined as a psychological pattern, model, or map we use to navigate our way through life. There's an old saying, we don't see things as they really are. We see them as we are, or how we have been conditioned to see them. These thought processes give us our opinions, okay? For example, I could bring up in a group, a large group setting, a number of things, politics, presidential candidates, abortion, all of these topics that you hear talk about today. And believe me, there'd be lots of opinions regarding these topics. And some people would hold very strong to those opinions. Those opinions are paradigms. And there's paradigms everywhere we look, even in the world of sheet metal stamping. For example, I like to use this. If I say to a group of people, see if you can solve this puzzle. Okay. 2 men died in a cabin in the woods. Now ask me as many questions as you possibly can till you think you have the solution. And many of the questions would be, oh, did they burn? Did a bear eat them? Did they starve to death? Did they die of disease? Did their cabin catch on fire? And all those questions. And the answer to each one of those questions is no, 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 no. It's interesting though, because if I say to a flight attendant or a pilot of an aircraft, the statement, 2 men died in a cabin in the woods, how did they die? They very quickly arrive at the point or the solution that their plane crashed. Why is that? Because when you say the word cabin to a flight attendant or a pilot, they instantly default to the airplane cabin because they have to do the pre-flight every day and they say the cabin this and the cabin that. Where most people, they think of a cabin as a little wooden structure in the middle of the woods with grizzly bears and pine trees. And so it's interesting how paradigms shape the way we come to conclusions. That being said, do I get to go to the next slide here? There we go. Okay, here are some typical paradigms that we have in the world of sheet metal stamping. Number one, Die making and die metal stamping is an art form. If you talk to any old tool and die maker that's been around for years and years, ask them, what is it that you do day in and day out? They'll try to their very best to explain to you what a tool and die maker is, or a die maintenance technician. And somewhere in that conversation, chances are they're going to mention, hey, this is an art form. You got to be an artist. Now, there was a time, certainly, and maybe in the history of these gentlemen you're talking to, where die making was an art form. In fact, if you look on the slide there, there's a book called The Art of Die Making. But keep in mind, that book was published in 1911. Needless to say, the process of designing and building a die as well as sheet metal stamping has changed significantly since 1911. And I wasn't around, of course, in 1911, but had I been, you would have seen an art form. You would have seen a process where people had to take a raw chunk of metal, tool steel, probably water hard at the time, and hand shape it using antiquated equipment and hand tools and grinders and disc grinders into whatever shape they were trying to make, maybe an automotive fender or a door or whatever it might be. So it required a lot of craftsmanship, the ability to look at something and shape it and visualize it. Hence the name, an art form. But today it's changed. We model up that car part in full 3D. We put it on a computerized, numerically controlled machine. We cut it within microns of its geometry, very accurately, very quickly. So there's not all of that hand shaping and things like that going on. So rather than viewing it as an art form, I would prefer that we view it as a science based on an understanding of sheet metal physics. I like to ask tool makers when I'm doing a public conference this question. By a show of hands, how many of you guys, and I'll ask you guys watching and gals, how many of you altered a die yesterday, put a shim under a block or ground on something or changed the shut height of the press or the cushion tonnage based on an inspiration you had earlier that morning? How many of you adjust the cushion pressure because it made you feel good or made you tear up or made you happy or sad or whatever it is? See, that's what I think of when I think of art, okay? And so hopefully we don't have guys out there making decisions and putting shims on blocks because it made them feel good. Hopefully, if you're doing that, you're doing it based on an understanding of why you're doing it. Okay. Another one. Only those with professional college degrees can be considered as professionals, right? We have a tendency in the United States to define professional career paths as those that have a high academic degree from university or college of XYZ. Negating the fact that we learn in lots of different ways. Okay. Now, keep in mind, I'm not trying to dismiss the importance of college. I have kids that go to college, and I'm an advocate for education. But keep in mind, just because you don't have a degree from XYZ doesn't make you not a professional. It is a professional career path. It's interesting, in a conversation with some PMA members this morning, we were talking about how Europe, Germany and specifically, views the tool and die and sheet metal stamping industry from a different perspective because their paradigm is different than in the United States. The next one, it's a dirty factory job. Some of the stamping plants I go into, you could literally eat off the floors. It's amazing, especially those doing stuff for the medical industry. I mean, literally, I could eat off the floors in those places. Everything is done through trial and error. There's the next one. No, everything is done by collecting data and using physics. You're doing computer simulations and understanding material behavior. Steel is steel. I'm very blessed to have Danny Scheffler right next to me, who metallurgically has probably forgotten more about steel than I know, okay? Very blessed to know him and use him as a resource for helping me when I'm trying to understand material issues. And one thing I know for sure, different materials require different processes, different presses, different lubricants, different tool steel, different ways of making a part. It's a different world. The next paradigm, when I tell people I'm a die maker, they say, oh, you must be really good at math. And I go, no, not really. In fact, I'm quite poor at math, okay? Because I think there's this perception that you gotta be super good with calculus or something to be a die maker. Yeah, of course I can do basic math. I hope I can, but I'm not, I don't know about the other panelists here, but I really doubt that even Danny Scheffler here has probably sat down and used a whole lot of calculus recently, okay? But there's that paradigm that's out there, okay? So here's the reality. Not the perception, the reality. Tool and die designing, building, engineering is a science based on physics, based on an understanding of physics. Dr. Stuart Keeler, God rest his soul, made a statement one time at a conference. He said, when sheet metal meets physics, physics always wins. Okay? It's hard to defy physics. And you know what? He's absolutely right. To be a good tooling designer, engineer, process engineer, or even to be a good tool and die troubleshooter, you have to have at least fundamental, if not extensive, knowledge of material behavior. It's not 1911 anymore, where we have 3 grades of steel, low carbon steel and thicker low carbon steel. You have to remember some of these paradigms were brought about as a product of history and tribal knowledge. Back when they made cars originally, they weren't concerned about fuel economy. If a part failed when you hit a tree, they just made it thicker out of the same stuff that they made it out of before. They didn't care about mileage, And so all of these rules that were established regarding die design, troubleshooting, they were created and they've been passed down from generation to generation to generation to generation. And unfortunately, a lot of them haven't changed. Case in point, what kind of clearance do you put between the punch and the die when you're cutting it? 10% of the material's thickness. Some of you are probably laughing right now because that's the value you use. I'm not suggesting it's wrong. I don't know what materials you're using, but materials have changed significantly. And chances are, if you're doing automotive work, that value is not even in the ballpark. But we still use it. Why? Because we've always used it. Why? Because we don't want to truly understand what changing that clearance is going to do, nor do we want to present ourselves with any risk. But once you learn, you can say, wow, that made a big difference in my process. It requires an extensive knowledge of material flow and stretch variables, part geometry. How does part geometry affect formability? How do the material properties affect it? Friction control. We have to understand tribology. Tribology is just the science of friction, if you don't know that. We have to understand tooling design and press related variables. Understand what role the press makes. I love to say, as it pertains to sheet metal stamping, the press is just as important as the die. I can build a jewel of a tool, with an accuracy that's unheard of. But if I put it into a glorified 250-ton trash compactor, I'm going to have issues. Okay? So we have to understand the entire stamping system, the material, the press, the feeder, the lubricant, all of that, the tool steel type, all of it fits together and everyone's a variable. And so we have to have a pretty good understanding of how it all works together. Why? Very simply, as I've stated, this ain't Kansas anymore, Dorothy. Okay, so if you're still using the same stuff that you used 20, 30 years ago, you might want to do a little research and educate yourself regarding how the industry's changed. For example, the Tin Man is no longer made of tin, okay? Okay, he's lighter, faster, and stronger than he's ever been. He's made out of high strength, low alloy, 80 XLF, dual phase 1100 material, martensitic steel, some certain grades of bake hardenable body panel aluminum and super alloys. He's got titanium joints and Inconel inserts in his back. And he's completely crafted. He's crafted completely different than he was 30, 40 years ago. He is crafted using lasers and water jets and CNC high-speeding machines that do hard cutting. Parts of his body are 3D printed, you know, and the stuff that does stamp out his arms are high-tech presses that are servo drive, ultra precision presses with parallelism and stroke lengths that are ultra precision. It's not 1911 and it's not an art form. So we have to shift our paradigm and look at it completely different. I told you I was getting my soapbox. Here's a classic thing that gives us our paradigms. And I'm not being critical, but Hollywood. Watch any movie. Try to find a Hollywood movie which depicts sheet metal stamping as a professional career path. Doctors see them all the time. Lawyers, firemen, policemen, all those movies that you see. When was the last time you saw a movie with stamping or tool and die makers in it? I remember one, Tommy Boy or whatever it is, okay, with the Callahan Brake Company, okay? You know, so now whether how they depicted it, I don't think it was a professional career path when they were trying to depict it, but you know, it's just the way we treat it, you know, and it's kind of sad. But, you know, all the other careers require high education, right? If you're an attorney or you know, whatever it is. And so, we got to look at things a little bit different, and we have to understand that difference. And how do we do that? We shift our paradigm, stop making die makers, stop making die makers and press technicians, and start making diologists. Now, there is no such thing as a diologist. That's a term I came up with. I named my company Diology because I firmly believe that the process of designing and building a die and stamping process is a science. So I thought diologist was a perfect fit. What separates a diologist from any other type of tooling specialist? A diologist is an individual that makes decisions based on an understanding of the physical behavior of sheet material and also uses data. Okay, I'm not going to make decisions because it worked last time. I'm not going to make decisions because that's the way we always do it. I'm not going to make decisions because I had success back in 1984 with a part that looks similar to it. I'm going to make decisions because I understand the physics that supports that decision. And if I don't understand it, I'm going to try my best to understand. Does that mean that a diologist always has the solution based on physics? Heck no. I can't tell you how many times I've stood out by a press, scratching my head and going, I just don't know what's going on here. I think if anybody's honest with yourself, you'd say every panelist out here has gone, this one stumped me, you know. But eventually we get there through the application of physics. Diologists avoid decisions based on what typical die makers do. And guys, I'm not picking on you if you're a tool and die maker. You're part of the family, right? But so many die makers make decisions based on, that's how I was taught to do it. They don't understand the physics supporting it. They only know if I increase that radius in the draw die, that it won't split. And that it worked on a part similar to it. But they're not really studying what's happening. How is that affecting friction? How is that affecting flow? How is that affecting a lot of things, okay? And so it worked last time. Oh, that's the way I was told to do it. There's another one. Oh, I've tried everything else. Trial and error, you know. I'll go into a company and say, have you put a flat spot on the top of that? Oh, we tried that. But did you try it right? There's lots of different flat spots, okay? How big a flat spot did you put on? And did you transition it into the radius and so on and so forth, okay? Or that's the way we've always done it. Products of tribal knowledge. You know, we go out and we talk to press operators and they say, hey, well, you just made an adjustment in the feeder. What was that adjustment? I don't know. They just told me if this happens to turn this crank a couple times and it'll stop happening. Okay. Now, did the problem get solved? Yeah. Did they understand why? And therein lies the bigger problem. Okay. So keep in mind, a dialogist might make some of the very same decisions that a tool maker or a tool technician or process engineer might make, but they make them based on an understanding of physics. And they answer that glorious word, why? Why? Explain to me why. When I was leading jobs and a plant manager at a company, tool makers would come to me and I would frustrate them because they'd say, hey, we want to do this to correct this in the die. What do you think? And I'd say, no. And they'd go, why? It worked last time. I said, yeah. And they said, well, you don't think it'll work? I didn't say that. All I was asking for them is to explain to me the physics that supported their decision. I didn't want them hacking on a die without telling me what's going to happen. So eventually they'd come back and say, okay, I'm going to increase the radius at the entry. It's going to reduce the friction, which will allow more material to feed in, reducing the strain at the top of the part, reducing the probability of splitting. Then I'd smile and say, thank you, knock yourself out. Okay, that's all I wanted. Okay, so I've only got a short period of time here, and quite honestly, my watch stopped working, so I don't even know what time I have here. But I kind of put together some courses that I think are very important to become a dialogist, as well as on the floor experience. Okay, number one, shop floor communication and leadership. I think it's so important that we have an understanding of how to communicate and how to get people to work together as a team. I rely on different paradigms. Guys, I'm sure any of the panelists would say, sometimes the solution to a problem is so simple, you don't think of it because you've trained your brain to think at all the advanced levels. And so you don't see something stupid like a rag clamped on the die in the press or, you know, something foolish. And so you have all these people with different levels of experience bringing different ideas and concepts to the table. And then you can come up with a solution. That's what consulting is. See, I think a lot of people think that a consultant is somebody that comes into their company and tells them how to fix stuff. And, you know, just like a blind squirrel that gets an acorn once in a while, sometimes that happens, but more often than not, it's a group effort. Coming in, getting people together as a team, collecting data, and we as a team find a probable cause or a solution for that problem. But it takes a good ability to communicate to individuals and instill compassion about what they do. I think it's very, very important. Basic math, we don't need to go through that. Metrology, yeah, guys, you got to read a micrometer and a height gauge and a few other instruments, okay? You know, basic metallurgy. What is tool steel? What is carbon steel? Again, you don't need to put marshmallows and toothpicks together and look at carbon diagrams because you're probably not going to make steel. Now, if you're going to go work at US Steel, yeah, you might do that. Introduction to sheet metal stamping. Okay, what can be made? You know, machine shop safety. Safety is part of everything, of course. Interpreting engineered drawings. Used to be called blueprint reading, but blueprints are kind of going away a little bit. There's still some people that use them, and if you need them, do blueprint reading. Introduction to machining processes. See, this is something that needs to change. People think tool and die makers need to be machinists. Oh, we have machinists. Tool and die makers today are die assemblers. They take block A that's already been machined, it's got the screws and the dowels in it, they set it where block A goes, they knock the dowels in, tighten the screws, and put it together, and off to the press they go. It's a different world. See, back with 1911, the die maker shaped the steel, set the steels apart, set all the pilots different distances, did whatever it was. So there was a lot more to it. Today it's been simplified. Where we really need the skill set is in tryout and troubleshooting and maintenance. Die types. What's a progressive die transfer die? You know, stage tool, automation methods, so on. Tool steel and coatings. That's important today. Keep in mind, the materials that we're using are very hard, high yield strengths, high tensile strengths, very abrasive. You know, we're almost at the point where we're forming tool steel with tool steel. That's quite a challenge, you know, and there's times when it just doesn't work out and we gotta heat the sheet material. We call it hot stamping, right? Press hardening. Friction controls, better understand lubricants and heat and friction and additives and how they affect, you know, friction. Understanding sheet material and coil. This is where companies like Danny Scheffler's company can help you out in understanding material behavior, N values, R values, strain distribution, so on and so forth. Drawing and stretching. What's the physics behind that? You know, metal cutting theory. How do I get the smallest or the longest punch life? And how does the material type, thickness affect those judgments? Die repair. Hey, stuff breaks. Okay. We'd like to believe that all we do is die maintenance, but you know, because we're human, press operators are humans, die makers are human, mistakes get made, stuff gets busted up. So we still got to know how to weld and put stuff back together and make parts. Measuring forming severity. I think it's important that people understand that there are means and methods of predicting failures before they happen to help us, you know, scientific ways of analyzing a part and you know, determining the corrective action by understanding specifically what's happening to the metal in that localized area. And some advanced math. I'm an advocate of teaching analytical geometry. Do tool makers use analytical geometry? No, probably not. Oh, we might use trigonometry once in a while if we're trying to do a, you know, a side chuck or something, get an angle right. So why is analytical geometry, I think, important? Because it teaches you how to think. It says, hey, angle B is this number, side A is this length, figure out what the length of this side or this angle is or whatever it might be. So you've got several things that you know, but one thing you don't know. The same thing happens in dies. You're looking at a drawing die, you got a split. You got 22 variables to look at. You know 19 of them. And you got to figure out, okay, what's the thing that's causing this failure or what combination of things are causing this failure? So you, and realize the interactivity. If you change this, this is going to happen. If you do this, this is going to happen. And so you have to analyze or perform what we call a cause and effect analysis to arrive at the solution. You know? And so there's a scientific approach based on physics. But you got to get there by analyzing all of the data and having the ability to think through. Understanding presses. You know, as I said, you know, the press condition, the type of press, the drive on the press, the size of the press, deflection of the press. You know, everything aside from the color of the press is going to affect your stamping process. And knowing what role that plays is very important. Die setup procedures. You know, many times people think that they have a tooling design issue when in fact it's just a die setup issue. You know, they don't have the pilot release set up correctly, or, you know, the shut height's wrong, or the pitch is incorrect, or, you know, the suction cups are not picking up at the right height, or whatever it might be in an automated process. And so part of die troubleshooting is understanding how the whole setup process is, because there's an activity between a defect in a body panel in the automation system. You know, if a suction cup comes down too low and picks up a body panel, it pushes on the metal, puts a dent in it before it picks it up. Somebody doesn't know that's going to figure out, think that the die must be putting a dent in it, right? And so they're not even going to focus on the setup procedure or the automation. Bending, flanging, curling, and extruding, ironing if you're doing that, making beverage cans. Lots of different things. And this is just an example, you know. I just threw a bunch of things out there. There's probably some that you might not do and some that you might do. In any case, in summary here, the key is we need to shift our paradigm from an art form to a science. We need to train and educate our new tooling professionals as dialogists, individuals that make good database decisions based on understanding. Okay. And then it's amazing what can happen, you know? And so I don't know if I'm out of time or not here, but thank you for listening to me. I'm sorry I got on my soapbox a little bit. I'm pretty compassionate about this, you know? I love the tool and die business. I love knowing that hopefully that what I share with younger individuals impacts their life in a positive way. So that's kind of what this is all about. Anyway, I appreciate the opportunity.
Thanks, Art. Yeah, great stuff. A lot to chew on there. A lot of process variables, and you know, as there's more process inputs as we've talked, and the materials get stronger, those inputs become even more critical, and the challenges become even greater. I'm curious, you know, Danny and Vince, based on what you see, you know, at Martinrea and Danny and the companies that you visit, some of what Art discussed here, and how much does that ring true with what you guys are experiencing when you're out in the field?
Well, Art, a lot of what you said this certainly makes sense, certainly fits with what I've seen, but you did make the comment asking about when if I still use calculus. And no, I don't use calculus, probably haven't in I don't know, 3 decades or so. But what I do use a lot of is Excel, because I can't do those hand equations. But more importantly, what I use is way too much at times is PowerPoint engineering.
Yeah.
But what's the importance of PowerPoint is communication. And to effectively communicate with your coworkers or with your boss, if you're trying to justify why you're making a change, you need some funds, you need to be able to effectively communicate all this vast knowledge that you know, because of course, you know a lot better than your coworkers. But if you can't communicate that, then the ideas don't go anywhere. And you also made the comment about making some tooling or process changes based on an inspiration. And I think many people out on the factory floor can relate to that, where you think you're not seeing enough metal flow, so you add some shims or you take away some shims to adjust the metal flow. Now that may or may not work depending on the situation. But what's critical is either way, communicate that to your coworkers. Write it down somewhere, because if unless you're working 24 hours a day, it may feel like it, but if you do have a second shift, third shift operation, if they don't know that there's a process change, then they don't know what has worked and what hasn't worked on that part. And if you don't document it, then you're going to bake in that same inefficiency on the next part that your shop's awarded. Or you just keep on making the same mistakes over and over again, waiting for somebody else to correct it. So I think a lot of what you said does hit home.
Super. Hey, thanks for that feedback, Danny.
Vince, how about Martinrea, in terms of process documentation, making sure everybody's on the same page? How much of a challenge is that?
Continual challenge day to day. I think every stamper, every plant fights that battle every day. And I think what compounds it is the term communication is evolving. And when you look at pre-COVID and post-COVID, the Zoom meetings are fantastic, but it still brings back the face-to-face and on the floor, and hey, come take a look at this. And as the problems are getting more challenging, I think the communication, exact problems to maybe somebody that doesn't understand it completely, focuses the emphasis on the communication in the right way. We struggle. I think everybody will struggle with that day to day, and when we can overcome that, as we overcome that, it'll get better.
I think we all agree it's important to tackle that challenge, right? Sure.
Even using the same terminology for the same effect at different plants, like smile, elongation, neck. weakness, thinning. Depending on where you are, what shop you're in, may have different definitions, different connotations, and inspire different courses of action.
Good, well, let's keep this moving. I know Danny, we really, again, we're gonna make sure we continue to shift this conversation and focus on the higher strength materials. And I know that you like to talk about how when the challenges, when the material gets stronger, the challenges get even bigger. All the challenges that aren't talked about become even more difficult to address when the materials get stronger. So I know you've got a few slides and some thoughts on that topic specifically.
Yep,
So
for sure, for sure.
You're on.
Great, thank you, Brad, and thanks for that talk there, Art.
Oh, thank you.
Yeah, as Brad alluded to, when we start dealing with stronger metals, we amplify the problem. Sometimes the problems just get bigger, but sometimes they're different problems that we didn't encounter before. Again, as a bit of background, my name is Danny Schaeffler, President of Engineering Quality Solutions. EQS is a sheet metal formability consulting firm, been around since 2002. Prior to that, I had a decade working for the second largest flat roll steel producer in the United States. The companies that we work with at EQS are metal formers, typically tier 1, 2, 3 in the automotive supply chain, or pretty much anything non-automotive. I've worked on projects with, of course, steels, aluminum, stainless, but also other types of sheet metals. Brad mentioned I wrote for MetalForming magazine. I wrote the Science of Forming column for 4 years, followed by 2 years of writing the Metal Matters column. My travels over the past 3 decades have taken me into lots of tool shops working on pre-launch activities related to die build, die buy off, as well as going into manufacturing facilities for troubleshooting, field formability analyses. With that as a background, I want to start off talking about the sheet metal grades that we have available. Maybe Art turned off my ability to advance the slides.
I was having a little struggle with it too.
There you go. Great. So I'm going to start with 1970s. And why am I starting with 1970s? Well, my co-panelists, although they may not have been working in the 1970s, when they were apprentices, they worked under people. They were apprentices under journeymen who got their knowledge base probably back in the 1960s and 1970s. And back then, there were typically 2 types of sheet metals that were in use, and that were collectively grouped as mild steels or a type of high-strength steel known as carbon manganese steels. Relative to the automotive industry, there were 7 unique sheet metal specifications where these 2 grade families came out of. I'm going to fast forward 30 years to the decade of the 2000s, where the not anymore 7 unique automotive sheet steel specifications, but over 100 now. And we have a plethora of new grades for, in the steel family, that's when the first generation of advanced high strength steels were commercially released. But we also see automotive applications of sheet aluminum alloys as well as stainless alloys. What about today? There are over 200 unique sheet steel specifications for the automotive industry alone. You see that we have more than just the first generation of advanced high strength steels. You may have heard that we're up to the 3rd generation of advanced high strength steels. Lots of different options that are available to manufacturing companies. But the uniqueness of these advanced high strength steels is that they're no longer basic commodities. They're actually highly engineered products that change in characteristics depending on which company and which location manufactures those products. The steel industry, and there's certainly examples with the automotive aluminum industries as well, But steel industry is continuing to expand. These are showing some recently completed as well as active future projects where you see that billions of dollars of investments and millions of new tons are coming on board now and in the very near future. These advanced high-strength steels are going to mean some changes to manufacturing processes. Even the most basic advanced high-strength steel that's been commercially available for more than 20 years now, dual phase 600, that's going to take an additional 20–30% of blank holder force. Hopefully you're going to have a way to apply that if you've been sourced on a part that is going to be made out of this most basic advanced high-strength steel. One of the characteristics of all of these advanced high-strength steels is that they work harden to a very strong degree, literally and figuratively. What that means is that as you're forming these higher strength products, they become even stronger. And that's going to have certain implications, because if you're dealing with a higher strength product that becomes even stronger when you're forming it, you're going to generate increased press loads, which means that your press has to have the necessary tonnage capability. But you'll also see that there's going to be additional temperature, even though you're only doing room temperature stamping. These forming processes will increase in temperature, and that's going to lead to the potential for lubricant burn-off. That's going to increase the amount of tool wear. As an example, you can see that this was based on a simulation, but verified with actual temperature measurements, again, for room temperature stamping. The friction from the contact of sheet metal with the punch and die material, for mild steel, it's going to heat up the sheet steel to 120 degrees Fahrenheit. Our lubricants that we are using are designed for that. But if we swap in higher and higher strength steels, you see that we're not at 120 degrees C, we're up to potentially 300 degrees Fahrenheit. I should say 120 degrees Fahrenheit. Now, depending on your strength, up to 300 degrees Fahrenheit. If you are not using a lubricant that is designed to have the additives functional at those temperatures, you're going to run into problems with additional tooling wear. So we also need to keep that in mind and change our tool design approach as we're starting to work with higher strength materials, higher strength steels, aluminum, and stainless grades. Those higher strengths will allow for a thickness reduction, which is great because that could lead to potential savings. But that higher strength means increased press loads and potentially increased tooling wear. But because we're dealing with thinner metals, that's now higher in strength, we have a greater risk of the tooling wear because these products are more prone to wrinkling. Now, remember, it's prone to wrinkling because they're thinner, but also we hopefully are going to have enough tonnage to hold it back in the binder. One of the challenges with these higher strength steels is an increased degree of spring back. Certainly that's the case if you're going to switch to an aluminum product, but also just in general, higher strength steels have greater spring back than lower strength steels. And that means you have the risk of tooling recuts when you're trying to do your tooling development to account for that. If we recut these materials so much, we now have the risk of our tool not being sufficiently stiff. So we need to account for that. And the sheet, I should say the tooling material that we use, we need to upgrade from our older strategy when considering that we're now dealing with higher strength metals, and the products are out there. Also, and Art alluded to this, with the higher strength metals that we're working with, those higher strength metals have a hardness that's approaching the tooling hardness. So now we have to ask the question, what is cutting what? Is it our tool steels that are going to be cutting or forming the metal, the sheet metal, or is it sheet metal that's going to be formed? Art also alluded to clearances, that 10% paradigm that we grew up with. Well, that probably worked well, and it did work well for mild steels. We've got decades of evidence to show that, but that's not necessarily the case as we go to higher strength products. For higher strength steels, we know we should be increasing that clearance above 10% if we're working with higher strength steels. However, how high that clearance is actually going to be a function not just of the strength level of the material that we're working with, but also the type, be it a dual phase steel or a complex phase steel, that are going to behave differently in your process. And in addition to that, it's going to be a function of the supplier who's providing that particular advanced high strength steel to you. There is one way to cut out a lot of the trial and error that Art referred to, and that's use metal forming simulation. When it comes to necking failure, most metal forming simulation softwares with the right inputs are really accurate to predict those, so you can actually do your trial and error on the tube. But where the challenge is on higher strength materials is the dimensional accuracy. Now, that for a while, for many years, that has been one of the downsides or one of the challenges with metal forming simulation. But that's even gotten to the point where simulation can fairly accurately predict your dimensional concerns, but you need to capture Young's modulus accurately. Now, if you've ever played in this space, you know Young's modulus of steel is 210, maybe 207 gigapascal. That's what we've been trained to think. Well, there is some variation based on grade. That does vary. But that 207 gigapascal is for the sheet metal that you get from your supplier. But what recent understanding is that as the metal is being formed, the modulus decreases. And for some grades, it decreases by 25% as you're forming it. If you cannot capture that into your simulation, you're not going to have the opportunity to predict your dimensional control to sufficient accuracy. But there are software packages that can accommodate those changes. And there's evidence where that has a dramatic improvement on the ability to predict dimensional precision. So I'm going to be talking about these topics and many more over a 2 days in-person seminar at PMA headquarters, as well as a virtual seminar in roughly 2 months in September 18th and 19th. You can see the QR code on the screen now, or you can go to PMA's website and look up the sheet metal stamping seminar coming up in September. So thank you very much for letting me talk in this. Turn it back over to Brad.
Thanks, Danny. A lot of good material there. Lou, do we have any questions from the audience at this point, or should we just?
We can continue, but yeah, please use the Q&A panel to ask us. We have a great panel here that would love to answer.
Good deal. I'd like to add one little thing to what Danny stated there about forming simulation and springback prediction, and he's absolutely right on target. I really appreciated that. One of the things that's a product of educating material behavior is understanding the root cause to springback. Now, I'm not at a metallurgical level that Danny is by any means, but I always tell people who are running forming simulation, keep in mind, it's not manipulating die geometries and input variables until you get all the colors that you just pretty colors and it all falls below the forming limit diagram. The first thing we want to do after we make a good part is analyze it and say, now what can I do to reduce the springback and do springback prevention as opposed to springback correction. So many people, they do multiple iterations of forming simulation until they make a part that holds water. Then they say, okay, it's good. Let's trim it and see the springback. Doom. Then they say, okay, let's build a die to compensate for the springback and bend it back the other way. When in fact, most of the problem could have been solved by going back to the stretching and forming operation and saying, oh, gee, the reason it's springing back is because I have very high strains right next to low strains. And all I have to do is add a draw bead in an area that didn't wrinkle, but I'm going to add a draw bead or put a bump in it to get the same amount of stretch localized. So, and then all of a sudden the springback problem gets you know, there's still always gonna be spring back. But the spring back gets a lesser value. But it's through only understanding sheet metal formability and understanding strain distribution and the root causes spring back that we can focus on spring back prevention and not so focus on so much spring back correction. Although correction is always gonna be there, you know.
Good, thanks for that. So I know we want to hear from Vince and what's going on at Martin Rea with the higher strength higher strength steel processes, but before we turn it over to Vince, we've got one last commercial message from our sponsor, Stamtech. So let's hear from Lee Ellard over at Stamtech for a couple minutes.
Hi, it's Lee Ellard with Stamtech here again. We're happy to be once again sponsoring the PMA and MetalForming Live. This is the second in the series. And I'm actually here at Stamtech today. Wanted to tell you a little bit about what we do here. We stock a whole lot of presses at Stamtech and press related equipment, such as the servo presses over here to your left. Got a really nice high-speed straight side press, 110 ton, 350 strokes a minute, which we just brought in recently. Got a whole bunch of presses in the back there, standard specification OCP gap frame presses. And down the other end of the plant, we've got quite a few straight sides and 2-point gap frame presses. We also stock feed lines to go along with our presses. So we sell quite a few of those. And down here, we've got one of the larger presses that we would bring in here, a 400 ton. We can stock up to 600, possibly 800 tons here in this warehouse, but that's a 400 ton that's currently sold. The slide next to it is another 400 ton that we're getting ready to stack up. So today's event is going to be about forming difficult materials such as high strength low alloy or HSLA and other exotic materials. So I'm going to cut to a short video right now to show you some stroke profiles in a servo press. This should be really helpful for you in forming these difficult materials. Thanks for coming. Hope to see you again sometime. Bye-bye.
Here's Vince to talk about how Martin Rea handles higher strength materials. Vince?
Thank you. Thank you for letting me have the opportunity to show you some of the recent activities and some of the technologies where we're using, deploying to make sure that we have a good understanding of the die system, the stamping tool, the simulations, and the press. This is a chart of coming out of one of our, I'll say, modern presses, modern tonnage monitors. And it's 4 corners of data. So you see 4 individual curves. There's it's a measure of the strain during a single stroke and a single strain, a single stroke of a high strength steel. And you can see up there's different loads over the press stroke on each of the corners. A lot of the times that one of the paradigms is you look at the tonnage monitor and it says 400 tons. And if you're in a 600-ton press, that's about as far as you need to go with your tonnage evaluations. But with some of the materials and some of the presses, what we're looking at, the dollar signs, the number of zeros for the decisions we're making are just getting so many zeros after the equation. It's, you have to pay attention to it. It's big dollars. So one of the things we're doing is taking a look at how much information, and this is something I'm sure you can go home today, go back to your press shop today and look at one of your modern presses and get this information. And hopefully what I can show is how you can make better decisions, knowing that this is information that's available to you today. One of the visuals that you can take out of this data, and looking at the left front corner and the right rear corner, you can see, you can isolate those two curves, and you can see that the it creates a very large torque on the press. This press is actually, because of the signal we're getting from the right rear, we know that the press is sticking. The signal shows that while we're applying tremendous force in 3 of the corners, it actually goes negative in the right rear. The white dot shows a negative force. So even though you have a very high-tech, high-strength piece of equipment, you can see by that some of the curves you get off the press, hey, we're abusing that piece of equipment, and you know, if we don't want the maintenance problems coming with tools being out of a line or presses being overloaded. This is one specific chart that can show, hey, look, there's an obvious problem. We're trying to bend the press, and you know, we can do better than that. The decisions for that, how to eliminate some of the eccentric loads. There are countermeasures for that. If we take the same press stroke and you look at it in terms of crank angle, through the press stroke, you can isolate where the centroid of the load is on the press bed. The graph you see with the blue clouds represents a real press bed, and the forces at each of at 10, I think it's 10 crank angle are shown at every 10, and it's represented by a single blue dot. And you can see that the vast majority of the points are not at 0, 0. And when you look at the press tonnage curves, when you look at the manufacturers, you know, you look at the directions, what they give you is our press is worth 3,000 tons at bottom if the load is being applied at the center of the press. And it's, I'll say, quite obvious by some of the positions of the dots on this diagram that loads are being applied outside of the 0, 0, and we need to be cognizant of the load placement on the bolster, and we need to be real cognizant of how high up in this press stroke that load is being applied. When we take those same press curves, the blue dots were a static look at that press stroke. The animation I'll play is watching the centroid of the load move around on the bolster. And if we take a look at, there'll be a dark green is the current position, and then 2 different shades of lighter green following it, to give you an idea of the the motion of the load on the bolster. When the dots change color to brown, is actually when the die is on bottom. So that you can see that even when the tool is on bottom, the centroid of the press force is not necessarily at the center of the press, and it's not necessarily stagnant. The where the green dots are in play is after the die makes contact with the blank holder, and you can see the load start off in this transfer press very far to the left on the feed side of the press, and you can see the load transfer. You can see the load start off during the press stroke, very far to the left. It bottoms, and as the die unloads, you can see the shift in the centroid through the stroke. I'm going to try to do that one more time. The load starts very close to the end of the bolster. It moves around. It moves while the die is closed, and then as the die is opening, the nitrogen cylinders and all of the die components are still applying the same force on the way up as it did on the way down.
Vince, quick question. Is that a function of the die or of the press?
The die that's in the press is what's exerting the force. The motion on the of the dot is the way the press sees the load of the die you have in the press. So nitrogen and all of the pressure pads, the forming of the sheet metal is what moves the dot around, the green dot around the bolster. And you can take that motion and put that in several different presses, I'll say electronically, and you can see how that same die, that same load pattern works out in, call it an assigned press, a press of record, and an alternate press or a future press, and see how the load will go into that machine, maybe a lower cost machine, maybe a higher speed machine, but you can make those same decisions based on data, not just the tribal knowledge, I think, as we call it. On this chart, the graphic is, the animation is going to tell the exact same story, but in its place on the bolster, it shows a representation of the press capacity. Simply, as the dot moves away from center, you can get a feeling for the 3,000 ton press can very easily be only worth 1,500 tons with the load far to the left or right, or front to back. So it gives you an indication of just how much the press capacity drops during the stroke. And you can see just by the motion of the same dots over the same bolster, you can get an idea of the magnitude that the capacity of that press is not necessarily 3,000 tons. I think for the duration of the press or the die working, the load is anything but on the center line of the press. As the material strengths get higher and higher, it seems like it can turn into a vicious cycle where the spring, the simulations are saying you're needing more and more force, and we'll have a couple of slides. I have a couple of slides that can show you the magnitude of some of the information, how we design in a lot of our tonnage. This particular graph, I'm really hoping to show a concept of four-dimensional press tonnage that I think we really need to start looking at it as we look at the higher and higher strength steels. When we say we're in a 3,000 ton press, you know, it's easy to say, well, we're only exerting 1,000 tons, you know, we got to be safe, but we're exerting 1,000 tons in an eccentric manner that can easily cock the ram on the press and abuse it through every stroke of its cycle. What I'm trying to show in terms of 4-dimensional is a component of that force has both a left to right and front to back as it moves around on the bolster, just like we saw in the animations. It also has a Z component where when we first see the first forces on the press, we're contacting nitrogen that could have 4, 5, 6 inches of travel, so that there is an XYZ component to that force. And really, we need to understand if our machines are capable in that X, Y, and Z. The 4th dimension is really time. The shape of that you see on the screen now is a 3-dimensional representation of what a particular press is at the bottom of its stroke. But that umbrella morphs as you get higher in the press stroke earlier in time. So really, we need to be looking more at just the total tonnage. You got 1,500 tons, you're in a 2,000 ton press. You have a 80% safety factor. You're all within normal operating parameters. Go ahead and run it. I think that with the dollar signs of the equipment and the costs that are running and what everybody is fighting for, efficiencies on the floor, some of these rebuilds or downtime that aren't planned can really affect your costs. This is a tonnage, 4 tonnage readings on a B pillar. The 4 tonnages in this particular graph are with and without sheet metal in the die. Those are represented by the 2 lighter curves, and then with and without the bottoming blocks. And those are typically the bottoming blocks. We all put that, we all know that when the die's on bottom, you have to have it all solid to the press. We know it induces tonnage on the press. That's things we live with. But do we really go through and understand, you know, is it really doing everything we say it is for quality? If we take a look at just the light curves, the 2, the light green and the light blue, that's without material in it. And what that really shows is the area under those 2 light green and light blue curves is the energy it takes to actually form the die you designed with the inputs from the forming simulations. In the very low left-hand corner of the curve, you can see change in the light and dark, and you can actually see the draw beads being set, and the area you know, further up on the graph shows the forming of the part. So you can see how much force our simulations are telling us we need to form a part. But when you look back, take one step back, and we have a tonnage problem. Is it the tonnage problem to form the part, or the tonnage problem to form the die with all of the current paradigms we have in it? And really, we have to take a look at the forming simulations that have been talking about. Really, we can look at that in these curves. The forming, the light blue box that has the predictable label on it is really the limitations of the simulation tools today. Up until during the press stroke in the simulation world, the simulation stops when the the relative movement between the upper and lower tool stops. That's when the die bottoms. In the predictable box, the far right corner or the far right edge is the when the die bottoms. And that is what you can predict from the forming simulations. The less predictable box is actually the tribal knowledge box. It's what ran like good last time. It's, you know, all of the results of all the shims. It's the result of what quality said they needed, but it's self-inflicted. The forming stopped a long time ago, and that it's just how much do you want to stretch your press and compress the die to make up for bad spotting in the tools, make up for coil to coil changes. That's really where your the tribal knowledge is, you know, how much tonnage do you really want to apply to make up for all the other variables that are on deck. When you can, and these are slides from another deck, and if there's interest, I can show you. This is simply the space being exerted, the energy being exerted from the nitrogen cylinders on a particular draw die as it's outlined from the forming simulation. And you know, in terms of, I forgot who mentioned it, we tried everything. Did you try, you know, and it's always, you know, it's always good. I always hear, I'd rather have too many than too little. Yeah, I get it. I'm from the same school, but did you try running them on half of the nitrogen that you designed in there? By and large, the tonnage problem you would have with this panel is not because it takes that much tonnage to form. It takes that much tonnage to be, that is designed in from the software, and the paradigms that might have gone into those original studies might not have been on these type of steels, and the continuous improvement is what we need to really concentrate on, and driving the synergy between the press, the die, the simulations, and the customer's needs. And yeah, I like the physics wins when you hit it, physics wins, and there's only so much press you can really afford in your stamping plants. And when we get into the bigger panels and the higher strength steels, it's not like if you designed it for the 4,000 ton press that you got the spare 6,000 press out back. You know, my wife says sometimes I need to read the directions. This is one of the cases where when you get into where your margins of error are so small, you really do have to look at the whole system together and really make informed decisions there. I really appreciate the opportunity to share those quick slides with you, and hopefully show you some of the things where you can go home today and look at the press strokes you have and see if there's room for optimization.
Well, thank you, Vince. We do have a couple questions.
Absolutely.
Presentation here. One of them it deals with earlier in the presentation with the load centroids.
Mhm.
And the question was, how can the load centroids be outside of the bolster? How far from the press center are the connecting rods? Seems as if some of the centroids may even be outside of the connecting rods.
They are, and that's what that makes the challenge even more even greater, is understanding that if your centroid load are outside the linkages of the press, you're really just trying to bend the ram around them. And then you wonder why you have to buy repair kits and linkages crap. And that's a really good question. I'm glad for that. These centroids of the load, when you look at it in terms of tilting, or in terms of, one of the first hits is the ram actually, cocks in the gibs, and you have large positive downward forces, and on one corner of the press, you have a negative upward force because it's sticking. And that really throws the visualization off, where given that loading scenario, the centroid of the load, what it's seen by the ram, is outside of the workspace of the die. And for sure, you should be adding a counterbalancing cylinder, something to shift the dies in the press, something to move that flyer, that particular motion of the ramp, and you'll get a lot more life out of the parts that are already in the press.
And another question regarding the loading point clouds, are they generated beforehand using simulation data, or those are actual?
No, those are actuals. Yeah, those are actuals. I've been really trying to work with one of the simulation package suppliers to try and look at how to go into, and I've wrote code that actually goes into the simulation, pulls out the simulated loads to see what it can, what those simulated loads do in the press. But it's really only 2D. It gives what the draw die is worth over time, what the restrike die is over time, but you really don't see the the fore aft front to back dimension in the simulation. We've been asking for that for a long time, but it just that hasn't evolved yet. The but you can get a good left to right vision of what the simulation says. And code I've written says, add some cylinders over here or shift the die. Even if you're running in a transfer die, you don't have to add things. If you have a trimming die on the exit side of the press, you can simply design in a couple of higher tonnage cylinders. So instead of in a trim die where you might need 30% of holding pressure, design in 50, design in 60%. And that way, when those pads come in, you're offsetting some of the load, and that you can move the, even though you're adding tonnage, the small amount that you're adding tonnage moves those point clouds to the center of the press, where you can really benefit from the tonnage you're paying for in the press. I hope that's tries to answer that question.
I appreciate it. Art, have you seen similar situations that maybe some of the companies you've visited, or Danny, that are dealing with these some of the steels that Vince is talking about?
Absolutely. I mean, Vince's presentation is very good and made it a few very good valid points, especially in today's world of high strength materials. We need to not only look at the way and the means of how we're going to take this flat piece of sheet metal and turn it into a part, but look at the tonnage requirements, not just overall tonnage, but how much tonnage are we going to use throughout the entire forming of this process, or the forming of the sheet material. There's no doubt, as Danny said, we're using different materials today. I said that to say Kansas anymore, right? The newer materials are thinner, lighter, stronger. It takes more blank holder force. Or blank holder force means greater force at a different point during the press stroke. And as you know, a crank drive press doesn't have full tonnage throughout the stroke. Most of it's pretty close to bottom dead center. And so, forming simulation will tell you, oh, well, it takes, 300 tons to make this part. And so you say, oh, that's no problem. I got a 400 ton press, negating the fact that 8 inches off the bottom, you need 200 of that 400 tons of press, and you don't have it. So it's not just available tonnage, but how you distribute that tonnage through, the whole forming process within that ram. Higher strength materials are going to take more tonnage, and more tonnage is going to abuse the presses if we don't focus on balancing tonnage and making sure we have the right equipment to do it. Plus, keep in mind, There's more shock with higher strength materials. And not just in cutting, but when you come down and hit that blank holder, there's gonna be a lot of shock. And so we can reduce that shock by investing into servo drive press technology to pre-accelerate the binder, blank holder, draw pad, whatever you wanna call it, on the downstroke to reduce that shock, reduce some of the wear on the presses. Even in progressive die design, we try to design the die to balance the forces throughout the whole die. Sometimes very difficult, but today we have to focus on means for balancing tonnage through adding cylinders on one end of the die or whatever it might be to try to make the tonnage as even as we can through the whole tool, especially when the tool just fits in the boundaries of the press. So very good presentation, Vince. Appreciate that.
I have a different perspective on that, you know, just from the places where I visited. I think the topics, everybody agrees tonnage is important, is the bottom line. But the shops that I go into, most of the people there acknowledge tonnage is important. Okay, do you have a tonnage monitor? That's kind of the basic question to start with. Do you have a tonnage monitor?
A what?
A what? Exactly. And if they have it, it's broken, it's in the corner over there. We haven't fixed it yet. It goes back to one of the things that Art said in his presentation. Data, collect the data. Data is important. The topics that Vince was going through showed how important that information could be. But if you're not monitoring it, you can't control it and you can't use it to your benefit. So I encourage any metal formers out there, break out your tonnage monitor, get it fixed, calibrate it, and don't just pay attention to the peak tonnage. Pay attention to the tonnage curve. Maybe you could get away with it. You probably have gotten away with it when working with mild steels. But each and every one of you is doing value-added stampings. Maybe you're still working with mild steels, but on a very complex design. Quite likely, you're using advanced materials on an advanced design for an advanced part. The reason for that is if you're not, the work's probably already in a low-cost country. So get the data that you can have access to and use it to your advantage.
That's that slide you showed with the cushion force. Are you changing the way you're designing in cushions into your tooling as we speak?
We're trying. There's still a lot of, how do you make a change in a very high dollar situation, low margin situation, and still protect? You know, can I still do it the way I wanted to? We'll try your way, but I want to have my way as a backup. And where costs level out, that's where some of the give and takes are. But certainly as you put in a brand new press, for those lucky enough to have the capital these days to do that, you want to know the limits because you're going to want that capital equipment forever. And yeah, you want to be able to have the data that says that what we're doing, it may not be good enough today as it was yesterday. Design your tooling where you are confident, but have the measuring paradigm to verify, trust but verify.
Yeah. Well, you're surely making this process a science, not an art.
Yeah, when you can take a little bit of the on our in God we trust, everybody else brings data. That's the data you need to go back to the die design team, the press team, and say, hey, this is really the tonnage I think I need. Is it safe for the system?
Very good. Well, we've reached the end of our scheduled time. Do we have any more questions from the audience, Lou? Or we
Did I actually have one that related back to simulation, actually, from Dean Phillips here about simulation accounting for like pitmans running left to right, opposed front to back, or things like that. If you could talk about, anyone can address something along those lines.
Beyond knowing that some software packages do take that into consideration, I'm not sufficiently well versed in each software to go into that detail. but I know that some packages do take that into consideration.
Well, good.
I'd like to add one more thing. One of the questions that people have been asking me lately is, where can we get this type of training? And of course, my company does offer that, but
As does Engineering Quality Solutions.
Yeah, fair enough. Maybe this is a little teaser, maybe a little premature here, but I am working with Precision Metal Forming Association and PMA EDU to create some online, potentially online, some might be on site, practical courses that would be, developed specifically for tooling personnel who are responsible for die troubleshooting, die maintenance, maybe even some processing on how we're going to take a flat piece of sheet metal into a finished part. And pending how things go with the United States Department of Labor, perhaps even create an apprenticeship program, maybe a 2-year program for tool and die maintenance technicians, tool and die troubleshooters, that allows them to access real world, value added, realistic applied training to their jobs, and hopefully become that dialogist we seek out. Anyway, that's our goal here. We've got some hoops to jump through. We're dealing with the U.S. Department of Labor, so you can imagine. So
We'll work on our 3-point sheet.
yeah, that's
Excellent. Thanks, Art, for that. All right, again, so that's a wrap on another episode of Metal Forming Live. I want to thank everybody for joining us online today. And of course, a huge thanks to our panelists, to Art, and Danny, and Vince. Thank you so much for joining us today. And our sponsors, as always, STEMTech, Shea Presses, Nidec Press and Automation, and Principal Financial. So please join us for the next and the last Metal Forming Live event in our 3-part series. If you're running press brakes, whether you're new to press brakes or experienced, I think you'll find some of the best practices that we're going to present during this session on August 6th to be very useful to optimizing your quality and productivity in press brakes. So please join us on August 6th. Again, thanks for joining us. Thanks to our panel, and enjoy the rest of your day.
Thank you.
Welcome back, my friends, to the show